In the late 1990s, astronomers made a discovery so shocking it rewrote our understanding of the cosmos. For decades, scientists believed that after the Big Bang, the universe's expansion would gradually slow down, its motion tugged back by the collective gravity of all its matter. It was a comforting idea, the cosmos expanding, yes, but gently easing into stillness over time. Then came 1998. Two independent teams observing distant Type 1a supernova, exploding stars billions of light years away, expected to find them slightly dimmer than predicted. What they found instead was something utterly baffling. These cosmic beacons were too dim. The only explanation? The universe wasn't slowing down. It was speeding up. Imagine it, a cosmic balloon, not just inflating, but doing so faster and faster, galaxies rushing away from one another at ever-increasing speeds. Gravity, the fundamental glue of the cosmos, was losing the fight. Something else, something invisible, was pushing the universe apart. This mysterious force was soon given a name: dark energy. A placeholder for ignorance, perhaps, but also a window into a profound cosmic truth. Roughly 70% of everything that exists, unseen and untouchable, is made of this enigmatic energy. It doesn't shine, it doesn't absorb light, and yet it defines the universe's grand trajectory. The discovery was so revolutionary that it earned its finders the 2011 Nobel Prize in Physics. But it also left us with a haunting question. What is dark energy? As we stare deeper into the night sky, watching galaxies drift apart like cosmic islands lost in an ever-growing ocean, we're reminded that the universe is not a static backdrop. It's a living, changing entity. And hidden within its silent expansion lies the most powerful and mysterious force we've ever encountered. So, what exactly is dark energy? The truth is, we don't know, but we have suspects, some bold, some elegant, and all deeply strange. The leading idea traces back to one of history's greatest minds, Albert Einstein. When Einstein formulated his general theory of relativity in 1915, he realized that gravity alone couldn't keep the universe static. To counteract the pull of gravity and maintain a steady cosmos, a belief almost everyone shared at the time, he introduced a mathematical patch called the cosmological constant. It was a term that represented an energy inherent to space itself, a kind of built-in push woven into the very fabric of the cosmos. But when later observations showed that the universe was expanding, Einstein scrapped his constant, calling it his greatest blunder. And yet, decades later, the blunder returned, no longer a mistake, but a possible key to understanding dark energy. Perhaps Einstein's cosmological constant was real all along, a quiet, ever-present force that fills space and drives it apart. This idea ties closely to something known as vacuum energy, the energy of empty space. Quantum physics tells us that even the void is not truly empty. Particles flicker in and out of existence in an eternal dance of creation and annihilation. Each of these quantum jitters carries energy, and collectively they could generate a repulsive pressure, precisely what we observe as cosmic acceleration. But there's a problem. When scientists try to calculate how much vacuum energy there should be, the result overshoots reality by a staggering amount, by a factor of 10 to the power of 120. That's the number 1, followed by 120 zeros, the most inaccurate prediction in the history of physics. So maybe dark energy isn't a fixed property of space. Maybe it's something dynamic, something that changes over time. Some physicists propose the existence of a mysterious field, nicknamed Quintessence, that slowly evolves as the universe expands. Others suggest we've misunderstood gravity itself, that perhaps, on cosmic scales, Einstein's equations need an upgrade. Each of these theories carries its own beauty and its own flaws. None have yet captured the full picture. For now, dark energy remains a cosmic placeholder, a name for something we sense, but cannot yet comprehend. A whisper in the equations, a shadow in the stars, hinting that the universe is far stranger than our minds can grasp. Dark energy isn't just shaping the universe, it's deciding its destiny. For billions of years, gravity and expansion have been locked in a cosmic tug-of-war. Gravity pulls matter together, building stars, galaxies, and clusters. Expansion pushes everything apart. For most of cosmic history, gravity was winning, at least locally. Galaxies formed, stars ignited, life emerged. But in the grand equation of existence, balance has tipped. Dark energy is now the dominant force of the cosmos, making up nearly 70% of its total content. It is silent, invisible, yet irresistible, stretching the very fabric of space faster and faster with each passing billion years. So what happens next? If dark energy continues its steady push, galaxies will drift so far apart that, one day, observers in the far future will see nothing beyond their own galactic island. The universe will become a lonely place, dark, cold, and eerily still. Astronomers call this the Big Freeze. In this scenario, stars burn out, galaxies fade, and time stretches toward infinity. But there are darker possibilities. If the strength of dark energy increases over time, its expansion could accelerate without limit. Eventually, it could tear apart galaxy clusters, then galaxies themselves, then stars, planets, and finally, atoms. Space would rip open in a catastrophic finale known as the Big Rip. There is also a far rarer alternative, the Big Crunch, where dark energy reverses its sign, turning from repulsive to attractive. The universe would halt its expansion and collapse inward, crushing all of existence back into a singular point. A rebirth, perhaps, or the end of everything. The data we have today suggests dark energy behaves like a cosmological constant, steady, unchanging. That means the Big Freeze is the likeliest fate. Still, in a cosmos, this vast humility is our only compass. Dark energy may yet surprise us. It may evolve, decay, or reveal a hidden pattern we've barely glimpsed. Whatever its nature, one truth endures. The universe's story is far from over, and its final chapters are being written by an invisible hand, one that shapes the stars, the galaxies, and the ultimate fate of everything we know. If dark energy is invisible, how do we hunt it? How can we study something that leaves no trace, no light, no shadow, no sound, yet bends the fate of the entire cosmos? The answer lies not in seeing dark energy directly, but in watching what it does. Every flicker of a distant supernova, every subtle shift in a galaxy's position carries a clue to its presence. It all began with those same Type 1a supernovae that revealed the accelerating universe. Astronomers call them standard candles because their brightness is consistent, like cosmic lighthouses scattered across space. By measuring how bright or dim these explosions appear, scientists can calculate how far away they are and how fast the universe is stretching between us and them. But supernovae are just one tool in a growing arsenal. The cosmic microwave background, the faint afterglow of the Big Bang, acts as a cosmic fossil. Tiny ripples in its temperature map reveal how matter and energy have interacted across billions of years, allowing cosmologists to trace the fingerprints of dark energy on the universe's grand structure. Then came the Dark Energy Survey, DES, a project that mapped hundreds of millions of galaxies using one of the most powerful cameras ever built. Over 6 years, DES charted how galaxies cluster and stretch under the influence of cosmic expansion. Each pixel of that map told part of the story of dark energy's silent reign. Meanwhile, the European Space Agency's Euclid mission launched with a singular purpose: to chart the dark universe. Euclid's sharp infrared eyes will peer 10 billion years into the past, capturing the slow unfolding of cosmic acceleration. And the search is far from over. The upcoming Vera C. Rubin Observatory, perched high in the Chilean Andes, will scan the entire southern sky every few nights, creating a dynamic movie of the universe in motion. It will catch exploding stars, shifting galaxies, and perhaps, just perhaps, new evidence of how dark energy evolves. Not far behind is NASA's Nancy Grace Roman Space Telescope, a marvel designed to map millions of galaxies with unprecedented precision. Together, these observatories form humanity's most ambitious effort yet to understand the invisible driver of cosmic expansion. We may not yet see dark energy, but with every photon captured, every data point refined, we are tightening the net around it, slowly revealing the contours of a force that has shaped everything since the dawn of time. After decades of observation, billions of dollars in telescopes, and countless sleepless nights of calculation, one truth remains: we still don't know what dark energy is. It makes up about 68% of the universe, more than all the stars, gas, dust, and dark matter combined, and yet it remains completely invisible. It doesn't interact with light, doesn't leave a trace in a lab, and refuses to fit neatly into the equations that define physics. Dark energy isn't just a mystery, it's a mirror reflecting the limits of human understanding. It reminds us that, despite our progress, the cosmos still holds secrets far beyond our reach. But that, perhaps, is its greatest gift. Because in every unanswered question lies the fuel for discovery. In every paradox, a doorway to a deeper truth. For scientists, dark energy is not a wall, it's a horizon, a place where knowledge meets wonder, where mathematics blurs into imagination, and where curiosity becomes courage. It forces us to ask, what if the laws of physics are only the first chapter? What if reality itself is more flexible, more alive than we ever dreamed? Someday, a new idea, a single elegant breakthrough, may reveal what dark energy truly is. Until then, the mystery endures, expanding with the universe itself. And as we look up into the night sky, watching galaxies drift into the dark, we're reminded that the universe isn't just something to study. It's something to feel, a vast, unfinished story, written in light, time, and the invisible force that drives it all.